Hello students, I am Dr. Parin Sheikh from LG Institutes of Applied Sciences. Today's video lecture is on Mossbauer Spectroscopy. This spectroscopy provides information of chemical structures as well provide information about the magnetic property of the material. In this video lecture, we are going to discuss about the Mossbauer effect. Okay. So let's start. The Mossbauer effect. What is Mossbauer effect? Nuclei in atoms undergo different type of energy level transitions. These transitions are generally related with emission or absorption of a gamma ray. Mossbauer spectroscopy is generated due to gamma ray. This energy level are affected by their electronic as well magnetic environment, which can change or split these energy levels. Changes in these levels can provide information about the atom's local environment within a system and should be observed using resonance fluorescence. Now, what is resonance fluorescence? Resonance fluorescence is a fluorescence from an atom or a molecule in which the frequency of emitted light is the same as that of light absorbed. Means the frequency of emitted and absorbed light remains the same. This can be understood by taking one diagram. This is diagram in which the gamma rays absorbed and gamma rays emitted, which having same frequency, that is absorption fluorescence spectra. Next, iron nucleus 57Fe is most used or studied in gamma ray spectroscopy, which is also known as Mossbauer spectroscopy. Other elements such as 129 iodine, 1119, 121 Sb are also frequently studied in case of Mossbauer spectroscopy. By the radioactive decay of 57 cobalt, its half-life is of 270 days. Isotope 57 is produced. With the help of energy level diagram, the information of iron nucleus 57Fe from cobalt nucleus 57 cobalt can be explained. Okay, this can be explained by the help of this diagram. In this diagram, nucleus in ground state having Z and N, and when nucleus absorbs the gamma ray and goes to excited state having the same number of Z and N. That means here electron capture process is done. That is gamma emission, which can absorb by resonant and fluorescence resonant is there. This can also understand by this diagram in which excited iron nucleus, here mentioned as Fe star, is produced by electron capturing of cobalt nucleus 57 cobalt. This radioactive cobalt has half-life of 270 days, which is generated in a cyclotron and diffused into a noble metal like rhodium, serves as the gamma radiation source for Fe57 Mossbauer spectroscopy. Now, excited Fe nucleus rapidly converts into ground state Fe by emission of energy. The energy change delta E is equal to 2.30 into 10 raised to minus 15 joule per nucleus, and the frequency of emitted gamma rays is equal to 3.5 into 10 raised to 18 Hz. If another Fe nuclear, that means absorber, which is in ground state, is introduced in emitted beam of radiation, it would be expected to absorb energy from the beam and to become excited the Fe star state. So here gamma radiation source is cobalt. Gamma radiation absorber, that is Fe, and the detector use, that is scintillator counter. Detection of this gamma ray can be done with the help of gamma ray detector. But detection of gamma ray is difficult due to following two major obstacles. First, the interactions between the nucleus and its environment are extremely small. This can also understand by the help of Heisenberg's uncertainty principle. Second factor, that is the recoiling of the nucleus as the gamma ray is emitted or absorbed, prevents resonance. For better understanding, in a free nucleus during emission or absorption of gamma ray, it recoils due to conservation of momentum. Means the frequency of emission and absorption do not remain the same, just like a gun recoils the firing a bullet with the recoil energy ER. ER is a recoil energy. This recoil is shown in figure 1. It is figure for recoil of free nuclei in emission or absorption of a gamma ray. The emitted gamma ray has recoil energy less energy than the nuclear transitions. But to be resonantly absorbed, it must be ER greater than the transition energy due to the recoil of the absorbing nucleus. To achieve resonance, the loss of the recoil energy must be overcome in some way. As the atoms will be moving due to random thermal motion, the gamma ray energy has a spread value of ED caused by Doppler effect, that is Doppler effect energy. This produces a gamma ray energy profile as shown in figure 2. To produce a resonant signal, the two energies need to overlap, and this is shown in the red shaded area, which is shown here. This area is shown aggregated as in reality it is extremely small. A millionth or less of the gamma rays are in this region and impractical as a technique. Okay, now what Mossbauer discovered that when the atoms are within the solid matrix, the effective mass of the nucleus is very much greater. The recoiling mass is now effectively the mass of the whole system, making ER and ED very small. If the gamma ray energy is small enough to recoil of the nucleus is too low to be transmitted as a photon vibration in the crystal lattice, and so the whole system recoils, making the recoil energy practically zero or recoil free event. In this situation, as in figure 3, if the emitting and absorbing nuclei are in a solid matrix, the emitted and absorbed gamma ray is the same energy. That means there is resonance. That means absorption fluorescence phenomenon. If emitting and absorbing nuclei are in identical cubic environments, then the transition energies are identical, and this produces a spectrum as shown in figure, a single absorption line. Here single absorption line we can see. So this is about Mossbauer effect. In next video lecture we will discuss about the isomer shift. Thank you.